Hello, this is another lecture on capacitors, and I'm going to recap some of what we talked about last time. Not go into a ton of detail. If you want to see more of the detail, you can look at the lectures from Tuesday. But I thought I'd start with a little practice, and you can read this problem, and if you want to read it and pause the video and see if you can come up with a solution, it's great practice. I'll do it right now. I want to find the capacitance of between two sheets of aluminum foil. Let's say they're the size of a football field. In other words, big. And I will, and I said 100 meters by 50 meters, separated by 1/10 of a millimeter. Imagine a capacitor that size. So I'm going to say, okay, the area of the capacitor is equal to 100 meters times 50 meters. That's equal to 5,000 square meters. Separation of the capacitors is 0.1 millimeter, which, doing the proper conversion, there's 1,000 millimeters in 1 meter. We get that it's equal to 10 to the minus 4 meters. All right, and so the capacitance in this case is equal to epsilon 0 A over D. And I'm assuming, since there's no dielectric stated, that the dielectric constant, kappa, is equal to 1 in this case. If there's no dielectric stated, you can assume that. So therefore, the equation becomes 8.85 times 10 to the minus 12 times 5,000 divided by 0.0001 meters. And then if you do all the math, which I do on the next page, I'll just simply go to the next page. Whoops, I guess I don't. All right, I thought I did. No, I do it on this page. I do it. We get about 440 times 10 to the minus 6 farads, which is about equal to 440 microfarads. And you could buy a capacitor this size, and it is not clearly the size of a football field. So there's techniques used to increase the capacitance using dielectrics, essentially, that are integrated into capacitors. Okay, so that was a little practice on the parallel plate capacitance formula. I also mentioned this last time, there's a video on it too. And I think there's a question on the homework about how much energy is in a capacitor. And you could calculate the energy, and it's in joules. And there's two equations that you could use, 1/2 CV squared or 1/2 Q squared over C. And check the units. You will see that the units will be joules. And we already said this too, larger plates and closer plates result in bigger capacitors. And we talked about why. Just looking at the parallel capacitance equation, you'll see that. And this again is that for parallel capacitances, the resulting capacitances simply add, and we derive that on a video that you can take a look at if you don't remember. So parallel capacitors are like series resistors. Similarly, for series resistors, I'm sorry, for series capacitors, I don't know if I have the equation in this one. I don't think I did. I'll just write it here just so you know it. It's like the one for parallel. This is again a review of last time. C1 and C2, if I want to combine these and create an equivalent capacitance, C equivalent is going to equal 1 over C1 plus 1 over C2. That's the equation when you have capacitors in parallel. So you see the last couple slides I was working with, because my writing covers it up. That's the first one, second one, third one, fourth one, fifth one for parallel capacitors, sixth one, parallel capacitors, seventh one, series capacitors. All right, I'm going to move on. And then a reminder about dielectrics, which we also talked about. They basically are something you stick between the plates of the capacitor that allow more charge to sit on the plates. And this is a model of the molecules of what happens in a dielectric where you have, if this is the positive side down here of the positive plate, and that's the negative plate up there, the negative sides of the molecules will align themselves towards the positive side of the plate and vice versa. So this brings even more negative charges closer to the positive plate, allowing more positive charges to want to come here if they're available, and the same for the opposite side. So it's basically a way to increase the capacitance of a capacitor. Here's a couple interesting and useful sites you can look on for the open the PowerPoint link up to these sites, and you'll see some nice videos, one of which you actually saw before, but it'll have more meaning now. And there's the simulation site that you can also take a look at that has capacitor simulations on it. There's a homework problem on the next homework that involves this. There's a video on this too. I'll just reiterate what that video goes through. It talks about what happens. Let's say you have a capacitor here, and you have it hooked up to a battery in one case. And then while the capacitor is hooked up, you then insert a dielectric. The question is, what happens to the capacitance? What happens to the charge on the plates? And what happens to the voltage across the capacitor? In the case where it's hooked up to a battery, well, every time you put a dielectric in, the capacitance is going to increase. That one's easy. And the other one that's easy is if you're attached to a battery, the voltage is going to stay whatever the battery voltage is. It can't change. It has to be V volts, whether you have the dielectric in there or not. So the thing that's going to change because of the capacitance is the charge in this case. The other case is if you have a capacitor hooked up to a battery, and then the battery is taken off. Okay, so now you just have a charged capacitor. Which has some amount of charge on its plates, same as it had even with the battery hooked up. But now you go ahead and insert a dielectric. Now what happens to the capacitance, the charge, and the voltage on the capacitor? So this case is a little bit different than if it's hooked up to a battery. In this case here, the capacitance, of course, is going to increase, just like it would if it were attached to a battery. The charge, however, has no place to go. The charge is going to stay there. The charge has to stay the same. So the voltage is actually going to be the thing that changes. When the capacitance changes, the voltage is going to change. So that is a little hint on, I'll just write this here, CQV. Realize you can't see this stuff down here. The capacitance is definitely going to go up when you insert the dielectric. The charge is going to stay the same if there's no battery hooked up. So I'll say without battery, charge stays the same. So then the question is, what happens to the voltage across the capacitor in this case? And so those are the two questions you'll see on the next homework that will give you some ideas in terms of how to approach. Okay, I'm going to stop this set of videos now, and we're going to get on to a new topic in the next video called RC circuits, where we put resistors and capacitors together and we see what happens. I'll get that one going shortly. All right, I realized I should show you the slides that are going to be covered with my writing. on the pages from the camera. So this was the slide we left on. Then I went on to talk about dielectrics. Looked at that slide with the molecules. This slide with the links that you'll have to access from the PowerPoint. Then the cases of the uh, what happens to the capacitor when you insert a dielectric with it attached to a battery and not attached to a battery. And then we're going to get onto RC circuits next. Okay, that's it.